So what we're going to have today is we're going to talk a little bit about quantum numbers part 2. This is Return of the Numbers. So far we've talked about Niels Bohr. Niels Bohr and his model of the atom, and he's not totally correct, right? We need to modify it just a little bit. And the reason we need to modify it is because of this guy, Max Born. Max Born was another German chemist. He's actually more mathematician than he was either chemist or physicist. And Max was taking a look at the hydrogen emission spectrum again. And what he did was he took it and he blew it up, right? So he examined one particular line, that violet line. And when he blew it up, what he saw was what originally people had thought was one line was actually multiple lines inside that one line. So he was thinking about that, and he realized that Bohr's model, where there is a level that the electron inhabits, is not the entire picture. There are also sublevels. So because of that, he actually proposed we need to change the drawing. And you can imagine, right, having already drawn some concentric circles, how crazy would it be if we had to draw multiple concentric circles, right? So we could show that there was a level, and then there's also sublevels within that. People would go nuts trying to do this. So what we do is we kind of put aside the Bohr model, and we show that there's a better way to indicate what's going on here. To talk about sublevels then, what we're going to do is we're going to realize, right? So right here is where you need to write a few things down, right? If you have a sheet of paper nearby, that's great. If you don't have a sheet of paper, you might want to grab one, and you want to write down a few things. You can pause the video. There you go. All right, so sublevels are inside of energy levels, right? So if you have an energy level, you can imagine that like a building, right? And inside of a building, you could have multiple floors. You could have multiple levels, right? So the energy level for the electron is the building. The stories or the floors are the sublevels that are inside that. An electron, when it goes into a level, it can go into different sublevels. Born showed that a level, right? Remember before we talked about how Bohr labeled all of his levels as n equals 1, n equals 2, that sort of thing. Well, if you're in n equals 1, you have one sublevel. If you're in n equals 2, you have two sublevels. If you are in n equals 3, you have 3 sublevels. If you're in n equals 54, there are 54 different sublevels. It's just the way the math works out. People didn't like describing these this way, though, because this takes a long time, right? You imagine I am in the n equals 1 level in the first sublevel, right? If we start looking at electrons, right, you imagine that atom that you guys drew the other day that had 81 electrons. Writing 81 sentences doesn't really make sense. So we had to have a shortcut way to do that. And the way we did that, I'm going to jump on over to the other side here. The way that we did that is that the sublevels all get a name. And Born was the person who named them, and he actually named them after lines in the hydrogen spectrum. So the first line in the hydrogen spectrum that everybody saw was that violet line. It was very, very bright, but also very thin, so they called it sharp. And the important part here is not necessarily where the name comes from, but the fact that we write that as a lowercase s. You can see the lowercase s right here. So the first one was sharp. The second line was the brightest line, and so it was called the principal line. So the second sublevel is called the P sublevel. The third sublevel is named after the third line, which is kind of wavery around the edges. They called it diffuse, and so we call it the D sublevel. And then the fourth sublevel was named after the last line. The red line was actually the thinnest and the toughest to see, so they called it fine. And so literally we call it the F sublevel is the fourth sublevel. There were only 4 lines that you could see. So after that, they ran out of names. So we got woefully unimaginative. And after that, they're all just named alphabetically. So after F comes G, then there's the H sublevel, the I sublevel, etc., etc. They've only just recently found some evidence of the J sublevel. And they think that maybe there's evidence of a K sublevel. But things get kind of weird when you get up to those higher sublevels. So when you put an electron into an atom, not only does it go into a level, but it goes into a sublevel. And if it goes into that first level, it can only go into the S sublevel. If it goes into the second level, it can go into the S or P level. And now you're starting to see if we go to the third level, it's S, P, or D. Again, we haven't shortened things all that much. We've just added a shortcut to say which sublevel we're talking about. So we need to take these sentences and we're going to make them even shorter. Oh, you'll love this. So what we're going to do is we're going to distinguish each of these sublevels. We put the level as a number in front. So whenever you write a sublevel, you write it like this. The 1s sublevel. That means I am in n equals 1, and I am in the s sublevel. If you look at the second level in the atom, you can have two sublevels. There's the 2s or the 2p sublevel, and so on and so forth. We'll come back to those again, don't worry. What Born showed, all right, what Born showed is that that there were sublevels, and it took a long time for mathematicians and physicists to actually figure out that the reason there are different sublevels is because there are different shapes of path that the electron is taking as it moves around the nucleus. The S sublevel was the simplest one, and it's kind of fun. It is a sphere. It's the simplest path that the electron can take around the nucleus. And here you can see pictures of the 1s sublevel. You see it's a small, tight sphere. The 2s sublevel is a little bit bigger, and that makes sense. Remember what we said before with the Bohr atom. As you move from level 1 to level 2, the electron gets a little bit further away from the nucleus, right? And that's what we see happening here, going from 1s to 2s, the sphere gets a little bit bigger. So the electron's still moving around the nucleus in a sphere, but what it's doing now is it's getting, that sphere gets a little bit further away. In 3s, it gets even further away. Don't draw these. Please don't draw these. I hope you're not drawing these. If you're already drawing these, great. I'm glad you practiced drawing your sphere. What you need to know is just the S sublevel is a sphere. And we say, this is kind of a math thing. I'm going to pull something from geometry. I'm just going to throw it out there. There's only one orientation for the sphere. If you have a sphere, it doesn't matter which way you turn it, it always looks identical. So we say the S sublevel only has one orientation. All right? It's the simple one. If we get more complex, we have to look at the P sublevel. Now the P sublevel looks like this. And I've heard this described a lot of different ways. Some people call it the barbell sublevel. Some people call it a lot of weird things. I call it the double drop sublevel because it kind of looks like two drops, kind of drop end to drop end there. And when you have them, if you notice, it's always centered on an axis. And so since there are three axes, the y, why start with y? The x-axis, the y-axis, and the z-axis, there are actually three orientations of the P sublevel. So again, don't bother drawing it, but know S sublevel is a sphere, one orientation. P sublevel is a double drop. It has three orientations. All right? And right here I can pause and I can say, can anybody think of how many orientations the D sublevel might have? Maybe, maybe, maybe. Maybe if we went from 1 to 2 to 3, and then, so 1 to 3 is adding 2, so we're going to go to 5, right? Yeah, that's exactly right. The D sublevel gets even weirder, right? You got more complex going from S to P, even more complex going to D. So these are a few representations of the D sublevel. How do you describe that shape? As a clover? Weirdness? I'm not sure. In fact, some scientists even argue that these aren't correct. There's an argument about another way to draw them. Knowing what they look like isn't really important. What's important here is to know that there are 5 orientations of the D sublevel. And go ahead and write it down. How many orientations would I expect for the F sublevel? Well, we go from 1 to 3 to 5. Add 2 more. You got 7, right? So we got 7 orientations for the F sublevel. What do we do with these orientations? Well, we're going to talk a little bit later on about a couple of guys that made this possible, right, when we start talking about orbital filling diagrams. But basically, the orientations tell you how many electrons you can put into a sublevel. So each orientation can hold 2 electrons. So we say that we look at each sublevel and we realize that the S sublevel then can hold 2 electrons because it's got 1 orientation times 2 electrons gives us 2 electrons total in the S sublevel. But the P sublevel has 3 orientations. So 2, 2, and 2 means I can fit 6 electrons. Oh, by the way, make sure you're jotting these down. S sublevel holds 2 electrons max. P sublevel holds 6 electrons max. The D sublevel holds 10 electrons max. And the F sublevel holds 14 electrons max. G holds 18. H holds 22, etc., etc. Where the most we'll ever really need to know in this class is F, because most of the rest of them are kind of theoretical anyways. And the way we write a sublevel is we give it a configuration, and that configuration, let's move me up to the top, there we go, looks like this, okay? And this is a nice shorthand. Basically, this is one long sentence that I've written in one tight shorthand notation. And that is that we have the 4th level, the S sublevel, and there is 1 electron in that. So level, sublevel, how many electrons are in that sublevel? So we can have legal or allowed sublevels. So for example, in n equals 1, the only thing that's legal is 1s. You can't have 1p or 1d or 1f. Literally, it's just the first. There's one sublevel, it's always the first sublevel. So if you look at n equals 2, it can have 2 sublevels, and it's always the first 2. We have 2s and 2p. N equals 3, we have 3s, 3p, and 3d, and so on and so forth. So if I want to draw something real quick on here, let's take a look at your assignment, right, is to go in and decide if something is legal or not. So for example, if I wanted to write something like, let's go with 5d 11, right? 5d11. Is 5d allowed? Yeah, if you keep going and you go to n equals 5, what we're going to see here, I'm sorry the handwriting is terrible, but we're going to get there, is 5s, 5p, 5d, and you could do these in your head if you didn't want to write them all down, 5f, and 5g, oh man, messed up on that one, 5g, there we go, 5s, 5p, 5d, 5f, 5g. All 5 of those are allowed, right? There's 5d. 5d's the third one. It's absolutely allowed. So no problem with 5d. What I need to do is look at this 11 part. So if I scroll back up real quick, 11, how many electrons can I fit in a d sublevel? Well, I can only fit 10 electrons. So if I look down here, 5d11, well, the 5d part's not bad, but what is bad is this part right here. I cannot have 11 electrons. It has 10 electrons max. So I could not have 11 electrons in the 5d sublevel. And that's your assignment right there. Go ahead and look at the sublevel notation worksheet, and you should be able to look at that and be able to find the answers, figure out the answers to that.